So here's some notes about section 3.3, just starting our polynomial function work, and I'm sure some of this is review, or if not all of it. So when we're dealing with polynomials, polynomials have the feature. I can know a function's a polynomial if there's no. So if there's no, like if I can't have 3 over x, that's not a polynomial. That's a rational function. We'll look at that later in this chapter. And the other thing that can happen is I want to have like 3i, 3i to the second. This has to be a real number. Now, it could be a decimal. Remember, I is imaginary numbers, and we'll talk a little bit about that this chapter also. But what makes a polynomial is it doesn't have those features. It also won't have a fractional exponent like this negative, here, let me change this to a different color. Negative 3x to the 1/5. Well, that's not a polynomial. That's actually a radical, fifth root, and that won't happen either. So they're going to have integer, positive integer. So like I won't have negative 3x to the negative 2. That would be, if you think about exponent rules, won't that be negative 3 over x squared? So again, a rational function. So those are all examples of things that are not polynomials. It's okay to have a fractional coefficient. In fact, why don't we talk about coefficients now? So coefficients are the numbers that are in front of the variables. So this negative 3x to the 5th term, so there's terms, right? And then you string the terms together to make the full polynomial. You could have one single term. You could have, if you just had a polynomial, if you had an equation that said, or a function that was y equals 3. Well, that's a constant. That's a polynomial. It just so happens it's a horizontal line also. But it's a polynomial with degree 0. The degree is the biggest exponent. And since there wasn't any exponent there, wasn't any variable there even, I knew the degree had to be 0. I knew the exponent had to be 0 because x to the 0 is 1. Okay, so let's step back here. So I see three terms. I see 3 terms in this polynomial. I see the biggest degree is 5. I know the leading term is the term with the biggest exponent. And so here, because the biggest exponent is 5, I know that's the leading term. So the leading term for that will be negative 3x to the 5th. And that leading coefficient is the coefficient of that term. So that would be negative 3. Okay, so there's a couple of things that do why this is important is the degree helps us determine what the function kind of looks like, and same with that leading term. Okay, so let's look at this one. I don't know if you printed the notes or if you have access to a printer, but let's look at, can I zoom this in a little bit? Yeah. So what do you think? What's the degree of this 3-term polynomial? Trinomial, we'll call it. What's the biggest exponent? I hope you said 4, so I know it's a 4th degree equation. I know the leading term, is that positive 4x to the 4th, and I know the leading coefficient is 4. Okay, so that's important to be able to recognize. Now we're going to use them. Okay, so I see, so they're looking for the long-run behavior. Now, what long-run behavior is, if I have a graph, and then I have some polynomial, I don't really care what happens in this area. I don't care what happens around the y-axis. What I want to know what happens is x gets really, really big, and as x gets really, really negative. So really big positive, and then I talk about what happens to the y, to the y value. So I know if it's an even degree, and I'm sure you've seen this before in earlier work. For this function, I see that it's a polynomial. I see it's a quadratic. I see it's degree 2. Now, anytime I have an even power function, even-powered functions either open up like this, with some stuff happening in the middle. Let's put an XY axis here. There's some stuff happening in the middle. I don't know what has happened there. I haven't analyzed that, but I do know that as x gets really negative or as x gets really positive, that's what that function is going to look like. Now, if it's negative, if there were negative 3x, that would be reflected around, think back to our work we did with transformations in chapter 1, that would reflect the the function around the x-axis. So instead of opening up, it would open down with some stuff going on in the middle. So now what we usually say, some notation that David Lippman and Melanie Rasmussen use in their book, and a lot of their textbooks do it, and it's actually nice and concise. When you talk about long-run behavior, you want to say, as x goes to negative infinity, what happens to y? Well, if we look at this blue function, as x goes to negative infinity, doesn't y go up to positive infinity? So we'll say arrow positive infinity. And as x goes out to positive infinity, y also goes up to positive infinity, because it says as x gets big, y gets big. If I were dealing with this red graph where it's been reflected, I would say as x goes out to negative infinity, y goes out to negative infinity, and as x goes out to positive infinity, y goes out to negative infinity. They both go in the same direction, okay? So there's that piece for that even degree function. Now what happens, so this is basically a transformed quadratic function. If you think back to those toolkit functions that we looked at the start, back in chapter 1. So it's a transformed quadratic function. And this is going to be some kind of transformed cubic function, because the biggest degrees is 3. So I know how those behave. Here, let me get rid of some stuff here. There. Okay. Sorry, I had to watch that. So I know normally cubic functions look like this. I know x cubed looks like something like this. Yeah, I know I don't have the curve quite right. That's not bad. So that's what x cubed looks like. So and x to the 5th works the same way. X to the 5th it'll just be steeper. It grows faster because it's a 5th degree. So that would be like x to the 5th. X to the 7th, same deal. So odd degree polynomials always look like this. So x goes out to negative infinity, y goes down to negative infinity. As x goes out to positive infinity, y goes out to positive infinity. They go in opposite directions. Okay. Now what can happen, and that's what's going to happen in this one, do you see how that leading term has a negative coefficient? That's going to reflect it around the y-axis, so that would reflect it this way. If it was negative x cubed, it would look like this. This has some other stuff going on. I really don't care what's going on around the y-axis right here. I do care about what's going on out at infinity. So let me clean some stuff up here, and we'll actually answer that g of x question. Okay, so for this g of x, I see it has a leading coefficient of negative 2. I know it's an odd degree function. So as x goes, so that means it's going to look like this, right? It's going to get reflected around the x-axis. So as x goes out to negative infinity, y goes up to positive infinity. As x goes out to positive infinity, y goes out to negative infinity. It's that easy. Now, this last one, I don't want you to have to expand this. What I do want you to do is see this. Again, let me clean this up. If I were to expand this all out, I would have a whole bunch of terms with it. One thing that I would get, not the shortcut way, is I know that this x minus 1 quantity squared, you'd write it out like this, and then you'd FOIL it out. Well, that would give me an x squared plus a lot of other terms, right? This one is just x plus 4. This one is just x. I know when I did all that distributing, I would end up with an x to the 4th, and then the leading coefficient would be negative 2. So I know the leading term for this polynomial is negative 2x to the 4th. And remember, out at infinity, all those other terms don't matter. It's just that biggest leading term, because when you're raising a big number to the 4th power, that's so much bigger than raising it to the 3rd power or the 2nd power. So this is going to be the term that rules out at infinity, out at big numbers. So how does this graph look? Well, without even graphing it, without doing any more work than I've just done, I can say as x goes out to negative infinity, it's an even power function, but it's been reflected around the x-axis, so I know it's going to look something like that. So as x goes out to negative infinity, y goes down to negative infinity. As x goes out to positive infinity, whoops, I should have written y here. Sorry, let me erase that so it's a little cleaner. Y goes to negative infinity. As x goes to positive infinity, y also goes to negative infinity because they head in the same direction because it's an even-powered polynomial. Okay, so without having to do any work, we can come up with that. So now in the next part, we know the ending behaviors. We know how to find the ending behaviors. To make a quick graph, it's also good to be able to find the x and y intercepts, right? The horizontal and vertical intercepts. And I know that any point, so let's draw an xy graph. I know that any point on this y-axis has the coordinate 0 and then some number y. So if I'm looking for the vertical intercept, really all I'm looking for is what's g of 0. Sorry, so I'm going to just drop in 0 into this mess. And if it's 0 minus 1 and 0 plus 3 and 0 minus 2, so that's going to become what? Well, let's see, 6 and times 2 is 12. So I know that y value is 0, 12. And I just found that by evaluating f of 0. Okay, now to find the x-intercepts, we want to know, so the x-intercepts, any x-intercept has the coordinates x comma 0, right? And then a different x, but I know y is 0. So here you're going to set the equation equal to 0. And what's nice about this one, this is already factored. So, and I know that it's called the zero product property. I mean, it's a formal name. But I know if x equals negative 1, doesn't this become 0? I mean, if x equals positive 1, that's 0, that's 4. That's negative 1, but because this one is 0, the whole thing is 0. So when x equals 1, that makes it 0. So that's an x-intercept. That's the x value of a horizontal intercept. Then the other one, what plus 3 is 0. What we're really thinking was what x plus 3 equals 0. So x equals negative 3. And then the same deal for this one, x would be 2. And it's okay, depending on what they're looking for, x equals 2. You could just write those x-intercepts here as x equals. If they're asked, if they read, this is more important for myope math, but if they say find the coordinates of the x-intercept, well, then you got to write it as 1, 0, 2, 0, and negative 3, 0. And myope math will expect you to usually put the increasing order. So I probably should have written this as negative 3, 1, and 2. Okay, and that's the x and y intercepts. It's not too bad, but we'll spend some time later on next week, next week you'll learn how to do the factoring. How can I figure out the degree from the graph? Well, one thing I can do, I could look at this ending behavior, right? Well, that looks like it's an odd degree. Now, so that means it could be something to the 5th power, it could be something to the 3rd power, it could be something to the 7th power. But because you're asking me for the least possible degree, I want to go with the smallest one, so 3. The least possible degree would be 3. Now, the other way to do this, if you think about the number of turns, those are always 1 less than the degree. So because there's 2 turns, it would have to be at least a 3rd degree equation. Now this one, I see an even degree, right? I know it's headed up in the same direction. I see 2 zeros, but I've got this wiggling stuff going on in the middle here. So that tells me there's something a little bit more than just x squared, right? So that's one reason why we want to look at the turns here. Let me get an eraser going. I see in this graph, I see a turn here, I see a turn here, and I see a turn here. So that tells me that probably has to be at least in x to the fourth. Okay, so what I did is I looked at the ending behavior, then I looked for the number of turns. And the number of turns are always one less than the degree. Well, can be at minimum one less than the degree. Let me word it that way, because it can have some other things going on. Okay, so I hope that's pretty easy. Then we're just on to the exercises out of the book, and as you can see, let's see, I think I've covered everything here. I haven't see the maximum number of turns. We've got that. How can you tell the number of turning points and another number of turns? I hope you said it has to be 4 because this is a 5th degree polynomial. Okay, it has obviously one less. Ending behavior. All right, so I think I'll let you do this. You can get the answers in the book, in the back of the book, or out at that David Lippin website. That's just erroneous. Well, you've got the textbook you can look at rather than this. I usually give my Oxbow students the exercises so they can keep it all together. Okay, I guess long enough video. Give me a yell if you need help.